Hello everyone. Today we will study permutation. A permutation is an arrangement of objects. Where the order of an object matters. Order matters means if I switch order for two objects, it makes difference. For example, if I arrange AB, it's not the same as BA. The order of object matters means if I switch order, it makes difference. Let's look at a simple example first. List all possible permutations of letters A, B, C. List all possible permutations of letters A, B, C. What can we do here? So all possible arrangement for A, B, C, it could be, we have A, B, C, that's one possible order. Another possible order could be A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. We can see that there are 6 possible arrangements. There are 6 possible permutations. Now, how do we calculate the number of permutations? How many different permutations are there? We can see that there are 6 permutations. But is there a way to calculate 6? We can see that there are 6 different permutations. But is there a way to calculate 6? We try to arrange all 3 letters, put them in orders. That means there are 3 places. 1, 2, 3. For the first place, it could be either A, in the first place, it could be either A, B, or C. If the first place is A, the second place could be either B or C. If the first place is B, the second place could be either A or C. If the first place is C, the second place could be either A or B. Then if the first place is A, second place is B, the third place must be C. So this arrangement is A, B, C. If first placement is A, second placement is B, the first place is A, second place is C, the third placement must be B. So that's an arrangement A, C, B. If first place is B, second place is A, third place must be C. So that's an arrangement B, A, C. If the first place is B, second place is C, the third place must be A. That's an arrangement B, C, A. If the first place is C, second place is A, third place must be B. So that's an arrangement C, A, B. If the first place is C, second place is B, then the third place must be A. That's an arrangement CBA. So we can see that if for the first place there are 3 choices for the first place, for each case on the second place there are 2 choices. Then on each case for the third place there's only 1 choice for the third place. So that's 3 times 2 times 1 that equal to 6. 3 times 2 times 1 can also be written as 3 factorial. So that's how we make arrangement for 3 objects. Here, let me introduce the first permutation rule. Permutation rule number 1, it says the number of ways to arrange n objects in a row is n factorial. That's permutation rule number 1. The number of ways to arrange n objects in a row is n factorial. This can be proved by using counting principle. This can be proved by using fundamental counting principle. Suppose we want to arrange n objects in a row. So there are n spots here. 1, 2, 3, 4, 5. I go all the way up to n. There are n spots here. In the first place, it could be any one of the n objects. There are n choices. Second place cannot be the same one, so it will be n minus 1. Next place cannot be the same as the first 2. So the number of choices will be n minus 2. Next one is n minus 3, and go all the way down. Eventually, since we arrange all n objects, in the last place there's only 1 choice. Second last will be 2 choices, and third last will be 3 choices. So n choice in the first place, n minus 1 choice for the second place, n minus 2 choice for the third place, and so on. The number keep going down until 3 to 1. The last place has only 1 choice. This is n factorial. If I multiply out, this is n factorial. That's the number of ways to arrange n objects in a row. So in the previous example, when we try to arrange 3 letters in a row, the number of arrangement is 3 factorial. Number of arrangement is the same permutation. So number of permutation is 3 factorial. Next example. Consider a group of 10 people. Part A. In how many ways can we arrange all 10 people in a row? In how many ways can we arrange all 10 people in a row? By permutation rule number 1, the number of ways to arrange 10 people is 10 factorial. By permutation rule number 1, the number of ways to arrange 10 people is 10 factorial. Next question. In how many ways can we arrange 7 of these people in a row? In how many ways can we arrange 7 of these people in a row? So try to arrange 7 people out of 10. Let's draw 7 spots here. 1, 2, 3, 4, 5, 6, 7. Let's draw 7 spots. In the first place, we have 10 choice. It could be any one of these 10 people. Second place cannot be the same one, so there are 9 choice. Third place cannot be the same as the previous 2, 8 choice. And 7, 6, 5, 4. If I try to write this in terms of factorial, it can be written as 10 factorial divided by 10 factorial goes from 10 to 1. But here we miss 3 to 1. So take 10 factorial divided by 3 factorial. 10 factorial divided by 3 factorial. 10 factorial is 10 times 9 times 8 times 7, go all the way down to 3 to 1. Here we go down, we only multiply from 10 to 4. What's missing is 3 to 1. So I divided by what's missing. 10 factorial divided by 3 factorial will be this. Next, let me introduce permutation rule number 2. The number of ways to arrange R objects out of n in a row is n factorial over m minus r factorial. The number of ways to arrange R objects out of n in a row is n factorial over m minus r factorial. How do we get this answer? We try to arrange R objects out of n in a row. So let me draw R spots here. Let's draw R spots for R objects. Suppose there are R spots here. That's the first object. That's the second object. That's the third. That's the fourth. Last one is the R's. The one before last one is M is R minus 1. That's the first object, second object, and until the last object. For the first object, there are n choice. Second choice cannot be the same one, so n minus 1 choice. Third choice, third place, for the third object we have n minus 2 choice. Next one we have n minus 3 choice. And for the last one, how many choice do you have? For the last one, how many choice? For the last one, for the last object, how many choice do you have? n minus 1, n minus 2, n minus 3. And for the last object, how many choice do you have here? Let's try to see the pattern here. For the second object, we have n minus 1 choice. For the third object, we have n minus 2 choice. For the fourth object, we have n minus 3 choice. We can see that this number is always 1 less than the index. This number is always 1 less than the index. So, for the last object, it will be n minus r minus 1. For the last object, it will be n minus r plus 1 choice. So m minus r minus 1 choice. Two minus 1 is 1. 3 minus 1 is 2. 4 minus 1 is 3. So r minus 1 is r minus 1. This can be rewritten as this expression m minus r minus 1 in parentheses can be rewritten as m minus r plus 1. So if I try to simplify this expression, what can we do here? If I try to simplify this expression, I have n times m minus 1, m minus 2, m minus 3, until n minus r plus 1. If I continue the sequence, I have, what do I have? If I continue the sequence, the next number will be m minus r. If I continue the sequence, next number will be m minus r, because the number keep going down. M minus 1 minus 1 is m minus 2. M minus 2 minus 1 is m minus 3. So number keep going down. M minus r plus 1, minus 1. When I subtract 1 from here, I get m minus 1. Next will be m minus r minus 1. If I keep going down, I'll go to 3, 2, 1. But when I multiply these many terms, I need to divide this many number to keep in balance. I need to divide this number at the same time to keep in balance. So this is the same as this. So here we can see that the numerator is n factorial. It goes from n down to 1. The denominator is m minus 1 factorial. That's how we get this answer. The number of ways to arrange r object out of n is n factorial over m minus r factorial. So in the previous example, you can see that here. The number of ways to arrange 7 objects out of 10 objects. On the numerator, we put 10 factorial, put total on the top. On the denominator, take m minus r. 10 minus 7 is 3. I can answer directly. If I use the formula, I can answer directly. Next, let me introduce a notation for permutation. This notation P and R represent the number of permutation when we arrange R objects out of n in a row. This notation P and R represent the number of permutation when we arrange R objects out of n in a row. That equal to n factorial over m minus r factorial. Note, for permutation, there's a special case. What's P and N? What does P and N mean? P and N represent the number of ways to arrange n objects out of n in a row, which by permutation rule number 1 we know as n factorial. Does it match this formula? We know by permutation rule number 1, the answer must be n factorial. The number of ways to arrange n objects out of n in a row must be n factorial. Does it match this formula? Let's use this formula to compute the answer, see if we get the same thing. If I use this formula, numerator is n factorial. Denominator is m minus r factorial, which is, in this case, is m minus n factorial. M minus n is 0. 0 factorial is 1. n factorial over 1 is n factorial. So it matches permutation rule number 1. The number of ways to arrange n objects out of n is n factorial. Next example. When 4 dice are rolled, if every die comes up a different number, how many possible outcomes are there? When 4 dice are rolled, if every die comes up a different number, how many possible outcomes are there? So 4 dice are rolled. 1, 2, 3, 4. If every die comes up a different number, how many possible outcomes are there? When we roll a die, the outcome could be either 1, 2, 3, 4, 5, or 6. And there are 6 outcomes for each die. So for the first die, it could be any one of the 6 numbers. there are 6 choices. For the second die, cannot be the same, so there are 5 choices. Third die, 4 choices, and the fourth die, 3 choices. If I write it in terms of factorial, if I write it as a factorial, I can write it as 6 factorial over 2 factorial. That's how we solve it using counting principle. Can we solve this problem using permutation rule? Let's reconsider the problem over. We have 4 dice. That's the first die. That's the second die. That's the third die. That's the fourth die. The possible outcomes for the dice are numbers 1, 2, 3, 4, 5, 6. Since every die can up a different number, so for every outcome, we assign a number to the die. For every outcome, we assign a number to the die. There are 6 numbers. We actually arrange 4 numbers out of 6 to the dice. We actually arrange 4 numbers out of 6 to the dice. Every time when we arrange 4 numbers to the dice, we have an outcome here. This means first die can up 1, second die can up 2, third die can up 3, fourth die can up 6. So for every outcome, we arrange 4 numbers out of 6 to the die. Yes. So if we use permutation, we have permutation 6, 4. That means 6 choose 4. If we use the formula, we have 6 factorial over 6 minus 4 factorial, which is the same thing. 6 factorial over 2 factorial. Next example. In how many ways can 12 balls be thrown into 20 boxes if no box will receive more than 1 ball? In how many ways can 12 balls be thrown into 20 boxes if no box will receive more than 1 ball? If we think of counting principle, there are 12 balls. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For the first ball, there are 20 choices. We can throw the first ball into one of the 20 boxes. There are 20 choices for the first ball. Second ball cannot go to the same box because no box will receive more than 1 ball. The second ball cannot go to the same box, so it has 19 choices. Third ball, 18 choice, 17, 16, 15, 14, 13, 12, 11, 9, 8. If I write it in terms of factorial, that's 20 factorial over 7 factorial. That's how you can answer using counting principle. But the thing is, if I use counting principle, there are too much counting here. We have to count 12 numbers. There are too much counting. There are too many countings. Can we use permutation to get an answer? Can we use permutation rule to get an answer? Let's consider there are 12 balls. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 balls. And we have 20 boxes. Let's number the box. Number the box as box 1, box 2, box 3, up to box 20. Let's number the boxes. If I write 5 here, means I throw the first ball into box 5. If I write 7 here, means I throw the second ball into box 7. If I write 13 here, means I throw the third ball into box 13. So there are totally 20 boxes. We choose 12 number and assign to the ball, which means I arrange 12 number in a row. I arrange 12 number out of 20 in a row. By permutation rule, that's P 20 choose 12. We arrange 12 number out of 20 in a row, which is P20 choose 12. If I use the formula, I have 20 factorial over 20 minus 12 factorial, which is 20 factorial over 8 factorial. Sorry, I'm miscounting here. It should be 10 and 9. So 20 over 8 factorial. We get exactly the same answer. But using permutation rule, we can get an answer quicker. Using counting principle, sometimes there are too much counting. For example, if there are 200 boxes, or if there are 120 balls, 200 boxes, then it will be too much counting. If we use permutation rule, we can get an answer immediately. If we use permutation rule, we can get an answer much quicker. So either way is okay. We can use counting principle, or we can use permutation rule to get an answer. We must get the same answer using both ways. Next example, number 4, part A. How many 3-digit strings are there? If every character is different. If every character in the string is different. How many 3-digit strings are there? If every character in the string is different. So for 3-digit string, we know there are totally 10 different digits. 0, 1, 2, up to 9. There are 10 different digits. To make 3-digit string, we arrange 3 digits out of 10 in a row. We arrange 3 digits out of 10 in a row. We arrange 3 digits out of 10 in a row. So if we use permutation rule, the answer is permutation 10 choose 3. And use the formula. We have 10 factorial over 10 minus 3 factorial, which is 10 factorial over 7 factorial. Part B. How many 5-letter strings are there? If every character in a string is different. How many 5-letter strings are there? If every character in the string is different. We know there are totally 26 letters. We choose 5 of them. We then arrange 5 letters in a row to make a 5-letter string. So there are totally 26 letters. We arrange 5 of them in a row. There are totally 26 letters. We arrange 5 of them in a row. So the number of ways P26 choose 5. That's 26 factorial over 26 minus 5 factorial, which is 26 factorial over 21 factorial. Using permutation rule, we can get an answer quicker. In general, using permutation rule, you can get an answer quicker. Example 6. Consider all 7-letter strings with letters A, B, C, D, E, F, G. without repetition. Without repetition means we use every letter exactly once. Without repetition means we use every letter exactly once. For the 7-letter string, we use every letter exactly once. First question. How many different strings are there? So, in order to make 7-letter string, we must use all 7 letters, which means we arrange 7 letters in a row. We arrange all 7 letters in a row. By permutation rule number 1, the answer is 7 factorial. Part B. How many strings contain a substring of AB? How many strings contain a substring of AB? That means AB could be anywhere in a string. Could be A, B, D, E, G, F, for example, C. Or it could be D, F, G, A, B, E, C, for example. AB must be in a string. It's called substring. How many strings contains a substring of AB? If we want to put AB together, we first of all group AB. I first of all group AB together. I treat this as a special character. I group AB together, treat this as a special character, and the rest by itself is a character. If we treat AB as a special character, and the rest individually is a character, we have totally 6 characters. In order to arrange 6 characters in a row, by permutation rule number 1, the answer is 6 factorial. The number of ways to arrange 6 characters in a row is 6 factorial. Part C. How many strings contain a substring of D, E, F? How many strings contain a substring of D, E, F? So similarly, if a string contains D, E, F, we must group these 3 letters D, E, F together, and we treat this as a special character. If a string contains a substring of D, E, F, we must group D, E, F together and treat this as a special character. So we have A, B, C, D, E, F, G. Then if I treat this as a special character, there are totally 5 characters. By permutation rule number 1, the number of ways to arrange 5 characters in a row is 5 factorial. Next. How many strings contain substrings B, C, D, and F, G? How many strings contain substrings B, C, D, and F, G? If we treat B, C, D as a substring, we must treat B, C, D as a special character. If a string contains a substring of B, C, D, if we want a string to contain a substring of B, C, D, we must treat B, C, D as a special character. And we also treat F, G as a special character. What's left is A, E, So if I treat BCD as a special character, I treat FG as a special character. There are totally 4 characters. The number of ways to arrange 4 characters in a row is 4 factorial. Next example. List all possible permutations of letters A, B, B. So let's make arrangement for these 3 letters. To avoid confusion, let me call the first B, B sub 1. Call the second B, B sub 2. To avoid confusion, let me call the first B, B sub 1, second B, B sub 2. So make arrangement for these 3 letters. If we make difference between B1 and B2, we can make arrangement for these 3 letters, A, B1, B2. Let's make arrangement. One possible outcome is A, B1, B2. A, B2, B1. B1A, B2. B2A, B1. B1, B2A. B2, B1A. So we know that when we make arrangement for 3 letters, when we make arrangement for 3 objects, the number of ways to make arrangement is 3 factorial. 3 factorial is 6. So we have 6 different arrangements for these 3 characters. But, however, since B1, B2, they both represent B, they are exactly the same. Since B1, B2, they both represent B, these two arrangements, these 2 permutations, they both represent A, B, B. And similarly, since B1, B2 they both represent letter B. These two arrangements both represent B, A, B. And same thing. The last 2 arrangements, they both represent B, B, A. So actually, we don't have 6 arrangements. That's only 3 permutations. We don't have 6 permutations. We only have 3 permutations here. There are 3 different permutations. ABB, BAB, and BBA. Part B. List all possible permutations of letters A, B, B, B. Consider this example. We have 4 letters A, B, B, B. In order to make arrangement, let's first of all make the B's different. Let's make first B to be B1, second B, B2, third B, B3. Then we can make arrangement for these 4 characters. To avoid confusion, we make these B's to be B1, B2, B3. Now let's make arrangement for these 4 characters. It could be A, B1, B2, B3. A, B1, B2, A, B1, B3, B2. It could be A, B2, B1, B3. It could be A, B2, B3, B1. Or it could be A, B3, B1, B2. A, B3, B2, B1. Or it could be B1, A, B2, B3, B1A, B3, B2, B2A, B1, B3, B2A, B3, B1, B3A, B1, B2, B3A, B2, B1, or it could be B1, B2A, B3, B1, B3A, B2, B2, B1A, B3, B2, B3A, B3A, B1, B3, B1A, B2, B3, B2A, B1. Or it could be B1, B2, B3A, B1, B3, B2A, B2, B1, B3A, B2, B3, B1A, B3, B1, B2A, B3, B2, B1A. For 4 characters, we know that the number of arrangement is 4 factorial. For 4 characters, the number of different permutation is 4 factorial, which is 24. So here we see 24 different outcomes. There are 24 different permutation. However, B1, B2, B3, they all represent B, which means all these 6 representation, they all represent A, B, B, B. All these 6 character, these 6 permutation, they all represent the same thing, A, B, B, B. The same thing. All these 6 permutation, they all represent B, A, B, B. And all these 6 representation represent B, B, A, B. And all these 6 permutation, the last column, represent B, 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 A. So we have only 4 permutations. There are 4 different permutations. There are 4 different permutations: A, B, 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 A, B, 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 A, B, and B, 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 A. There are only 4 permutations. We don't have 24. We only have 4 different permutations. Is there a way to get this number 4 without actually list them out? Same thing for part A. Is there any way to get the number 3 without list everything out? Let's observe the first example. Observe part A. For part A, there are 2 objects. There are 2 objects which is indistinguishable. These 2 B's, they are indistinguishable. We can't make any difference between these two character B's. If they are indistinguishable, that means if I switch these two characters, it makes no difference. if I switch these two characters, it makes no difference. There are totally 6 factorials. There are totally 6 permutations. There are totally 3 factorial, 6 different permutations. If I make change for 2 characters, it makes no difference. And the number of way to make change for 2 characters is 2 factorial. The number of way to make change for 2 characters is 2 factorial. So take 3 factorial, divide by 2 factorial, I can get 3. That's how I get 3 different permutations. And for part B, there are totally 4 characters. When we make arrangement, the number of different arrangements is 4 factorial. But the thing is, we have 3 objects. They are indistinguishable. This BBB, they are indistinguishable. They are indistinguishable. That means if I make change for these 3 characters, it makes no difference. If I switch orders for these 3 characters, it makes no difference. And the number of ways to make change for 3 characters is 3 factorial. The number of ways to make change for 3 characters is 3 factorial. So take 4 factorial divided by 3 factorial, we have 24 divided by 6, which is 4. That's how we get 4 here. There are 4 different permutations. Next, let me introduce permutation rule number 3. Given a total of n objects, if there are m1 objects of type 1, m2 objects of type 2, and so on, then the number of ways to arrange all n objects is n factorial over m1 factorial, m2 factorial, and so on. So, for example, if there are totally n objects, m1 of type 1, m2 of type 2, and so on. If m1 objects of type 1, that means if I switch order for these m1 objects, it makes no difference. If I switch order for these m1 objects, it makes no difference. And the number of ways to switch order for m1 objects is m1 factorial. And similarly, if there are m2 objects of type 2, when I switch orders for these m2 objects, it makes no difference. And the number of ways to switch m2 objects is m2 factorial, and so on. Let's redo number 7. Part A. How many different permutations of letters A, B, B? So here we know that there are totally 3 letters. 2 of them have the same type. There are totally 3 letters. 2 of them have the same type. Then by permutation rule number 3, there are totally 3 letters, 3 objects. 2 of them have the same type. That's how I get 3. Part B. how many different permutations of letters A, B, B, B. If we apply permutation rule number 3, we can see that there are totally 4 letters. 3 of them have the same type. That means if I switch these 3 objects, it makes no difference. And the number of ways to switch 3 objects is 3 factorial. So 4 factorial over 3 factorial. 4 factorial is 24. 3 factorial is 6. 24 divided by 6 is 4. If I ask you a different question, how do you answer this question? If I ask you a different one, in how many different permutations of letters A, B, B, C, C, C? How many different permutations of letters A, B, B, C, C, C? So here we can see that we have a total of 6 letters. Two of them have one type. 3 of them have a different type. So use permutation rule number 3. There are totally 6 letters. 2 of them have one type. 3 of them have different type. For these 2 objects, if I switch order, it makes no difference. And the number of ways to switch 2 objects is 2 factorial. For these 3 objects, if I switch order, it makes no difference. And the number of ways to switch 3 objects is 3 factorial. So together, 6 factorial over 2 factorial over 3 factorial. Next, let's look at a different example. How many different strings can be formed using all letters in the word Mississippi, MISSIPPI, Mississippi. How many different strings can be formed using all letters in the word Mississippi? So we try to make arrangement for all these letters. There are totally how many letters? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are totally 11 letters. There are totally 11 letters. We have a total of 11 letters. We have letter I 4 times. We have letter I 4 times. We have letter S 4 times. We have letter P twice. So by permutation rule number 3, we try to arrange all these 11 objects. And so it's 11 factorial over 4 factorial for these 4 i's. 4 factorial for this 4s, and 2 factorial for these 2 p's. If I switch order for 4 i's, it makes no difference. The number of ways to switch 4 i's is 4 factorial. If I switch order for this 4s, it makes no difference. The number of ways to switch 4s is 4 factorial. And if I switch order for these 2 p's, it makes no difference. The number of ways to switch 2 p's is 2 factorial. And use your calculator, you can get an answer. Next example. when 10 dice are rolled, in how many ways can we obtain 2/4, 5/6, and 3/1? When 10 dice are rolled, in how many ways can we obtain 2/4, 5/6, and 3/1? When we roll a die, we obtain a number between 1 and 6. When we roll 10 dice, we obtain a list of numbers from 1 through 6. So there are totally 10 objects in a row. There are totally 10 objects in a row. When we roll 10 dice, the outcome is 10 objects in a row. And we have 2/4, 5/6, and 3/1. If I switch the order for 2/4, if I switch order for this 2/4, it makes no difference. If I switch order for this 5/6, it makes no difference. If I switch order for this 3/1, it makes no difference. That's the number of ways of obtaining 2/4, 5/6, and 3/1. Use calculator, we can get an answer. Next. Fourteen cards of the same type. Are packed in a row. Fourteen cards of the same type are packed in a row. If 4, 3, and 7 cards, if 4, 3, and 7 cards are white, blue, and red, respectively, how many distinct arrangements are possible? Fourteen cards of the same type are packed in a row. If 4, 3, 7 cards are white, blue, and red, respectively, that means there are 4 white cards, 3 blue cards, and 7 red cards. How many distinct arrangements are possible? So when we make arrangement for all 14 cards, the way to arrange 14 objects is 14 factorial. 4 of the cards have the same type, so divide by 4 factorial. The number of ways to switch order for these 4 cards is 4 factorial. And there are 3 blue cards. The number of ways to arrange these 3 blue cards is 3 factorial. 7 red cards. The number of ways to switch order for 7 red cards is 7 factorial. Then that's an answer. Next. In how many ways can we put A shoes into 4 class sets? In how many ways can we put A shoes into 4 class sets? Assume we put 2 shoes on each class set. So there are totally 8 shoes. We try to put it in 4 class sets. Assume we put 2 shoes on each class set. Assume that's the first class set. That's the second class set. That's the third class set. That's the fourth class set. For each class set, we put 2 shoes inside. That's the first shoes, second shoes, third, the fourth, the fifth, the sixth, the seventh, and the eighth. So we try to arrange all 8 shoes in these 4 class sets. The number of ways to arrange 8 objects is A factorial. The number of ways to arrange 8 objects is A factorial. But when I put the shoes in the class set, if I switch order for these 2 shoes, it makes no difference. If I switch order for these 2 shoes, it makes no difference. If I switch order for these 2 shoes, it makes no difference. And if I switch order for these 2 shoes, it makes no difference. So divided by 2 factorial, 2 factorial, 2 factorial, and 2 factorial. That's permutation rule number 3. Next example. In a school, 100 calculus students are assigned to 4 classrooms to take a test. 30 go to room A. 20 go to room B. 35 go to room C. And 15 go to room D. In how many ways? Can the students be assigned to take the test? So there are totally 100 students. We try to assign these 100 students into 4 classrooms. So the number of ways to assign 100 students to 4 classrooms. Think of this. That's room A. That's room B. Room C. And room D. We can consider we assign 35 students to room A. So assign 30 students to room A, 20 students to room B, 20 students, 35 students to room C and 15 students to room D. We actually make arrangement for these 100 students, but for the students in room A, if I change their seats, if I switch their order, change their seats, it makes no difference. Same thing for these 20 people in room B, if I change their seats, make arrangement, it makes no difference. And for these 35 students in room C, if I switch their order, it makes no difference. And for these 15 students, if I switch their order, it makes no difference. So that's 100 factorial over 30 factorial over 20 factorial over 35 factorial over 15 factorial. That's permutation rule number 3. If I make arrangement for the objects, it makes no difference. We need to divide by the number of ways of making arrangement. So for these 30 people, if I switch their order, it makes no difference. For these 20 people, if I switch their order, it makes no difference. For these 35 people, if I switch their order, it makes no difference. And for these 15 people, if I switch their order, it makes no difference. So that's an answer. Next. In a standard deck, of 52 cards, in how many ways can we distribute certain cards to each of 4 players? In a standard deck of 52 cards, in how many ways can we distribute 13 cards to each of the 4 players? So we distribute 13 cards to the first player, certain cards to the second player, 13 cards to the third player, 13 cards to the fourth player, so no card left. We distribute all the cards. So the number of ways of making this arrangement is there are totally 52 cards. 13 to the first player. So if this player gets 13 cards and he switches the order of the card in his hand, it makes no difference. If this first player gets 13 cards, he switches the order of the cards in his hand, it makes no difference. Same thing for the second player, if he switches the order of the cards in his hand, it makes no difference. Same thing for the third player, the fourth player. That's an answer. Next. In a standard deck of 52 cards, in how many ways can we distribute 5 cards to each of 2 players? In a standard deck of 52 cards, in how many ways can we distribute 5 cards to each of 2 players? So there are totally 52 cards. If I distribute 5 cards to the first player, 5 cards for the second player, we have 42 cards left, which means I actually split 52 cards into 3 groups, which means I actually split 52 cards in 3 groups. For each group, if I change the order of the cards, it makes no difference. For each group, for the first player, for there are 5 cards on his hand, if we switch the order of the cards, it makes no difference. For the second player, if we switch the cards on his hand, it makes no difference. And for these 42 cards on the deck, if we switch the orders, it also makes no difference. So there are totally 52 cards. We make arrangement for 52 cards. For these 5 cards, if I switch order, it makes no difference. For these 5 cards, if I switch order, it makes no difference. For these 42 cards, if I switch order, it makes no difference.